Thank you. Thank you. So I know that you are late, and now it's 5:10, and I have been asked to provide 5 minutes of presentation, so I will be very brief. But here I will talk to you about, the diversity, because I have diversity in research. You have seen here on the board 4 segments. There is the plasma engineering, there is the shielding under dry cask, there is the corrosion studies, and the non-intrusive sensors. I could stop like here, but I will give you a flavor a little bit. So the first one is the plasma engineering, and I have 2 important parts in the plasma engineering. Electrothermal high energy density plasma is a passion. We have been working on this, me and John Gilligan, for quite long time. And it has so many applications. It is a source that can provide high heat flux for determining the surface survivability. And also, it is a very good simulator for the disruption and the quench phase in future fusion reactors, as you can see in the upper one. It is also a launcher with which we can launch many projectiles, like, for example, it can be a fueling mechanism for fusion reactors by accelerating frozen deuterium to speeds in excess of 3 and 4 kilometers per second. This experiment, there is an experiment that's currently residing in Oak Ridge National Laboratory. It is 100% our design, and my student, Jonathan Coburn, is just shuttling on weekly basis between here and going to Oak Ridge, and then flying to San Diego to expose samples in the San Diego in the General Atomics 3D reactor, and coming with the assessment of how materials can survive in such environment in fusion reactors. This is operational with very high current. You can see the current here in the range of several kiloampere. It is also essential when we started this research. It was supported by the Department of Defense as one of the launching techniques, and as I speak right now, the first ever to be installed on a ship. It's now operational, and we carry the credit for being, providing all of the studies that we provided over years. I will move very quickly to the atmospheric plasma. Atmospheric plasma is a subject that's fast expanding. You have heard a lot from Dr. Shannon. You have heard also a lot from Dr. Stappelman about the atmospheric plasmas and how atmospheric plasma can serve in agriculture, in water purification, and in medicine. I'm involved in this research, and this is the device that we designed and developed, and it currently resides in the College of Natural Resources after moving it from the College of Textiles. We were doing this functionality for textiles, making a textile to be highly antimicrobial, insect repellent, fire retardant, name it. I will give you just a very quick example showing you how the surface modification can provide high antimicrobial, and this is a strain of E. coli, and this is pre and after the exposure to plasma. This picture was taken also inside of the device, where we have samples of cotton on the top, and down here it's part of vegetables, and we used this to provide sterility and provide the mortality to arthropods. If you look carefully, you will see that there are insects inside. This is enough for this now, and I move to the second thing. The second thing is on the shielding and the dry cask, and I became very interested in all of the shielding and the dry cask for about several years ago. And here, as Professor Morty mentioned about that the dry cask has the inner canister where the spent fuel goes inside. Our interest is in the coating techniques that can go around the inner canister, and it can provide single, double, or triple layers. Each one is responsible for a specific feature. And then we have the concrete overpack. So we are sensitizing this form of deposited technique, and in the meantime, we are investigating the overpacks. And that's why me and Dr. Jacob, we are involved in a strong effort in synthesizing concretes with different aggregate, with different materials, and we have a major activity with a company with the name Armacab that we are doing this research. So you can see that, of course, when we compare all of the forms of the coatings, we can see which one can perform better. Similarly, in synthesizing the concrete, we can show that, for example, as the overback thickness increases and we have the ordinary concrete versus a concrete, we call it concrete 6 because we don't want it to talk much about its composition, we can see that it actually performs much better. In the meantime, we do modeling as well. So we model the entire cask, and we can get all of the results in order to compare two experiments. Now we move to the third thing, which is corrosion studies. As long as we have all of these materials, we needed to understand the corrosivity and the passivation of all of these coated surfaces. We do this into electrochemical technique, these known as the Gamma units, in which we expose the samples inside and in a certain brine with a certain pH, and then the flow of the current and the voltage coming from the controller, which is a potentiostat, and we get these kind of sets of graphs. These are the cyclic polarization, and we can vary the temperature. Then we can solve for the equations, and we can predict the amount of corrosion per year, because you want, of course, to have this to survive for 300, 400 years. However, we also look into the corrosion in terms of submersion into circulators, where each circulator has a certain brine at a certain pH, and then we can start looking into the corrosivity and either when any corrosion observed. And here you can see that this is 40 days, for example, running all the time. This is ongoing, and it's a very interesting research. And so you can see that all of the work that we do for corrosion is still related to the work on the first slide and the work on the second slide. Then we move here to the non-intrusive sensors, and the sensors are important subject. Dr. Guy just mentioned that sensors and developing sensors is an important thing. We have this as a concept for the sensors where the sensor is not embedded inside of any volume. It depends on wave theory. It depends solely on transmitting and receiving a form of ultrasonic wave that's excited with laser beams. And if you look to the top, you can see that we are launching the wave at a certain point, and then we have the receiver at the other point. Anything here in the propagation is function of the temperature and the function of the pressure and the function of the flow. So you can see that from these graphs, we can determine the temperature without being intrusive inside. Similarly, we can get also a measure of have the piezo crystal launching a surface wave. Surface wave is propagating and going all the way to where, can distinguish between water of the level. We are developing a system, an experiment in order to experience all of this. And actually, Mr. Sean Kerrigan is here, and he is the one who is instrumenting this kind of, device where it circulates the flow and it varies the temperature, and then the sensors will be from outside and it will be calibrated and tested. I think we will be able to do this probably by next month to run the first test. This is all what I do, and thank you for listening.